Hey everyone, today we'll unpack the nuclear and radiation physics that make a PET scanner work. PET stands for Positron Emission Tomography, and it's used to map function, not just anatomy, where tissue is consuming glucose, making proteins, or showing abnormal receptor activity. That's why PET is widely used for cancer detection and staging, checking treatment response, and many brain and heart studies. First, the nuclear part. A positron emitting radionuclide. A PET scan starts with a radiotracer, a biologically active molecule labeled with a radionuclide that decays by beta plus positron emission. The classic example is fluorine-18 in FDG, a glucose analog. In beta plus decay, a proton in the nucleus converts to a neutron, emitting a positron and a neutrino. Choosing the isotope is nuclear engineering. You need a workable half-life, enough positron yield, and positron energy is low enough that the positron doesn't travel too far, because that travel distance blurs where the signal started. Next, antimatter meets matter, annihilation, and conservation laws. After emission, the positron slows in tissue, mainly by ionization and excitation, pure electromagnetism. When it finally meets an electron, they annihilate. Conservation of energy and momentum means their rest mass energy becomes photons, 2 times 511 kiloelectron volts equals 1022 kiloelectron volts total, and most often that appears as 2 511 kiloelectron volt gamma rays emitted in nearly opposite directions. The nearly is important. Tiny residual motion produces slight noncollinearity and Doppler broadening, setting a hard physics limit on resolution. Now the radiation transport problem, where 511 kiloelectron volts photons do in the body, those gamma rays have to escape the body. At 511 kiloelectron volts in soft tissue, the dominant interaction is Compton scattering, so photons can be deflected and lose energy. If a scattered photon is detected, it can point back to the wrong place and create false uptake. That's why PET systems apply an energy window around 511 kiloelectron volts to reject many scattered events, and why modern reconstruction explicitly corrects for scatter and attenuation to keep PET quantitative. So how do we detect the photons? Detector physics. The scanner is a ring of detectors designed to stop 511 kiloelectron volts gammas efficiently and timestamp them precisely. Most systems use dense scintillation crystals, materials chosen for high density and high atomic number, so 511 kiloelectron volts photons interact quickly. A gamma interaction deposits energy. The crystal produces a fast flash of light, and photodetectors, PMTs historically, increasingly silicon photomultipliers, convert that light into an electronic pulse with a measured energy and time. Here's the signature trick: coincidence timing. PET doesn't aim like a camera, it uses timing. The system looks for 2 detector hits within a tiny coincidence window, typically a few nanoseconds. If they arrive together, we assume they came from the same annihilation and draw a line of response between the 2 detector elements. One event gives a line, not a point, but millions of lines from many angles let Reconstruction algorithms solve an inverse problem and estimate the 3D tracer distribution. Real data includes backgrounds. True coincidences are the clean case. Scatter coincidences involve Compton-deflected photons. Random coincidences occur when 2 unrelated photons happen to arrive within the timing window. Add detected dead time and high count rates, and you see why PET needs careful physics-based corrections. Why modern scanners love time of flight. TOF PET. TOF PET adds another conservation or lever. If you can measure a tiny difference in arrival times, you can localize the annihilation to a shorter segment along the line of response. Better timing resolution directly improves image, signal to noise, and lesion detectability, especially in larger patients or low count scans. Finally, why PET is often paired with CT. In PET/CT, the CT provides an anatomical map and, crucially, an attenuation map that can be transformed into a 511 kiloelectron volts correction that boosts quantitative accuracy and lets clinicians match PET hotspots to precise anatomy. Summary: PET is a chain of physics. Beta plus nuclear decay produces a positron. Annihilation turns mass into 2 511 kiloelectron volts gamma rays. Radiation transport through tissue is dominated by attenuation and Compton scatter, and high-speed detector plus coincidence timing converts photon pairs into lines of response that computers reconstruct into a 3D activity map. Nuclear physics, electromagnetism, and computation.